VLSos here. This is a video lesson on polynomials. We visited polynomials in the past. We're going to go a little bit further today. Let's take a look at some functions that are familiar to us. I'm going to define the g function as 2x minus 7. And we know this to be a linear function. Its graph is a line. Another function, h of x, 4x squared plus x minus 1, we know this to be quadratic. Very simple cubic function, parent cube is x cubed. And we could also go back and include a very simple function like 3, which we would call a constant function. All of these are different functions in that they belong to different families. And their graphs have very reliable features. Lines are always straight. Quadratics are always going to be parabolas and curve just once. Cubics are going to curve one more time than a parabola. But all of these functions belong to what we call a family of functions called polynomial. These are all polynomials. What makes these polynomials? Well, polynomial is a function that follows a few rules. Polynomials may have any amount of terms, and those terms are powers. If we take a look at our functions here, and these are not the only polynomials possible, we could keep going with this list and have a power term that has x to the fourth, x to the fifth, and so on. But the ones that we have listed here, we can see that every term is a power. And if we're looking at the constant terms, like -1 and 3, we can think of those as powers as well. We can think of this 3 or any constant times a power whose base is the variable and exponent is 0. And the reason why we can think of it that way is because anything to the 0 is 1, and we don't have to show a constant times 1. We don't have to show the multiplication by 1. But we add it back in to understand that even constant terms are or can be thought of as powers, and thus belong to polynomials. The linear function that I have here has 2 terms in it. We could also call it a binomial, bi for 2, 2-term polynomial. This constant term and the cubic term have or functions have 1 term. They're monomials. This quadratic is a polynomial that has 3 terms. We could say that it is a trinomial. Polynomials also must have whole number exponents. A whole number is an integer, but not negatives. So if we look at these polynomials in every single term, focus on the exponents, the cubic has an exponent of 3, that's a whole number. So is 2. If it's not shown, it's 1. And if it's a constant term and we have to add the power to see that it's there, it will have an exponent of 0. 0 is a whole number. So when we have a term that has a 0 exponent, it also belongs to the family of polynomials. What we don't see here is any negative exponents or fractional exponents or exponents that have a decimal point. Polynomial can also have any real number coefficients. Coefficients are the numbers that multiply the variable component, in this case 3 and 2. Constant term is also a coefficient, though sometimes we refer to it as the constant coefficient. Again, because a constant term can be thought of as multiplying the power whose exponent is 0. So in this case, the constant function, the 3, can also be thought of as a coefficient. So what about non-polynomial terms? What makes something not a polynomial? Well, anything that breaks any one of these rules. For example, any equation that has a 1 over x term or includes it is not going to be a polynomial. 1 over x, if we use a power property, can be thought of as x to the negative 1. And negative 1 is not a whole number, so it can't be an exponent and also be a polynomial term. Functions, any trig function like cosine of the variable is not a polynomial term. It's not a power. 3x to the negative 2 is a power, but again, has a negative exponent, not a whole number, so it's not a polynomial. Ix squared, if we mean I to be the complex unit or the imaginary number that we're going to get more practice with. If I isn't a value, if it is a variable or the imaginary unit, the square root of negative 1, it's not going to be a polynomial. We throw that in now so that we can anticipate when we use I in the future that it is not going to make a polynomial if we use it. Another non-polynomial term, negative 3 to the 3 halves. It's not this negative coefficient that is the problem. It's the fact that we have a fractional exponent that then doesn't simplify to a whole number. And 3 to the x is a power, but it's an exponential function. So the exponent isn't even a number, it's a variable itself, non-polynomial. We have a term called degree to describe something about a polynomial function. What we call the degree of a polynomial is its highest exponential value. So we look to all of the exponential values within a function, within a polynomial, and we determine its degree by observing the highest one. This cubic function is a polynomial. It has a highest exponential value of 3. It only has one exponential value. It's 3, so this cubic function has a degree of 3. In the quadratic function, we've got a term with the exponential value of 0, 1, and 2. 2 is the highest value amongst those, so this quadratic is degree 2. The linear function is degree 1, constant function is degree 0. And if we think about it, the degree of a polynomial then also describes what family it belongs to. Quadratics will always be degree 2 polynomials, because if we had a term that was higher than it, it would no longer be quadratic. It might be cubic. And if a quadratic function is missing any squared term, it's no longer quadratic, it could become linear. So the degree of a polynomial is very useful. It describes an essential nature of that polynomial. We can use the concept of the degree and what it describes to very quickly understand qualities of polynomials, of complicated graphs. For instance, let's imagine that we are working with a graph like this. Pretty complicated mathematics. It's curving all around. But we can easily observe by the nature of this curve what kind of polynomial it is, what kind of degree it is, and then we can use the concept of the degree to start understanding something about the expression or the equation that this polynomial must, or this graph must come from. So what's the degree of this polynomial? We have a trick or a tool. If we can imagine a line on the graph, we could place this line anywhere we wish, but we place the line such that it intersects the graph as many times as possible, then the number of intersections that we observe is equal to the degree of the polynomial. So if I put my line here, this pencil representing a line, then I'm intersecting this graph twice. But that's not as many intersections as I'm able to find. I could place the line here and intersect at a maximum 4 times. The degree of this polynomial is 4. The maximum number of intersections that I can find with a line. If I have a degree 4 polynomial, then I'm going to expect at a maximum 4 solutions. If I had the equation of this graph and I set it equal to any value, then I should expect to find for my variable 4 values. Here's a familiar, hopefully familiar way of understanding this. The x-intercepts of this graph are the places where the value of the function is 0. If I had these values, then I could write my polynomial in factored form. These are the values of the x-intercepts. So if we call this the f function, here's what I could write with these 4 values. I could write the factored form in which I place each one of these x-intercepts into a factor. If the x-intercept, this value, is a, that's an x value in the domain. If I know what it is, if I call it a in general, then I can form the factor x minus a with it. Because if this is a 0, it means that when I put this value in for x, then the value of the function is 0. If this is a factor and multiplies the rest of the function, then this factor having a value of 0 will multiply and make everything else 0. This is the 0 product property that we've used with quadratics quite a bit. And I can continue this with every x-intercept. An x-intercept becomes a 0 of the function by making the factor x minus that x-intercept. Again, if I knew the value of this point and called it b, and I put that value b into this factor, then it would be b minus b, which would be 0. And if we multiply that by the rest of the polynomial function, whatever it is, it will turn the polynomial into 0. I can form 2 more factors. X minus c will also produce a 0, and x minus d will also produce a 0. So knowing the x-intercepts of a polynomial can make its factored form. And if I knew those values, a, b, c, and d, and put them into the factored form, I could multiply all of these factors and produce the equation in distributed form of the polynomial. So with a little bit of knowledge, we can construct the equation. We could also go in the opposite direction with that logic. For example, if I start with the equation of a polynomial, in this case, k, I'm going to call the polynomial k, and I'm going to have its factored form. And I set the factored form of this polynomial to 0, then this is what the 0 product property can do for me again. I can begin to graph. I know that I'm going to have an x-intercept wherever any one of these 4 factors is 0. So if I put in an x value of -3, it'll turn the -3 plus 3 into 0, which multiplies everything else, and the function will equal 0. -3 is an x-intercept. I will have an x-intercept at -1 as well, because putting -1 into this factor will produce a 0 factor. I will have a 0 at 1, and another one, my last one, at 5. This is a 4th degree polynomial, just like the previous example, because if I was to multiply these factors out, then one of those terms would be x multiplying itself 4 times to produce the highest exponential value of 4. This is a degree 4 polynomial. I should expect 4 solutions, and I'm going to have, if I set this equal to 0, those solutions as x-intercepts. So what do I know about the rest of the graph of this polynomial? It's either going to start below the horizontal axis and curve to go through those 4 x-intercepts, or it will start above and curve in the same way, but in the opposite direction. The graph of the polynomial, or the sketch of it, is either going to be start low and curve and end low, or start high, curve, and end high, but it will go through these points. It's x-intercepts that I was able to find. So which is it? Well, I'm going to do a little bit of analysis. I'm going to think, if I put 0 into this function, then am I going to get a positive or negative value? If I answer that question, then I know whether I'm going to be on this curve with a negative value if I put 0 into it, or on this curve, which is going to have a positive value at 0. How do I determine that? I already know the formula in the factored form, or the function. So if I put 0 into here, I'm going to have a positive number. 0 plus 1 is going to be a positive number. 0 minus 1 will be a negative number. And putting 0 into this factor will produce another negative number. So without knowing what these values are, I could multiply the values, but what I care about is whether I end up with a positive or negative number. When I multiply 2 positives and 2 negatives, I will end up with a positive value. So I know that when I put 0 in, I'm going to be on the version of the curve that is positive at 0. That means that the graph of this polynomial, or the sketch of it, is going to look like this, and not the other that it could have been. So I've used the nature of polynomials in degrees in order to very quickly understand something about the graph given the function in factored form. Very quickly, I was able to determine a fairly complex graph, including all of its x-intercepts very accurately. Likewise, if I have a graph of a polynomial, even if it's complicated, then with some conceptual understanding of what it means to be a polynomial, I can know something about the equation of that polynomial very quickly.